Hello friends, let us now learn some important points about the ultrasound. In the ultrasound, we will learn about the transducers. Ultrasound transducer. So, different types of transducers we will learn in this lecture. A transducer is an image, is a device, and this is the picture of transducer. And this transducer will convert one form of energy into another form of energy. So, in ultrasonic transducers, will mainly convert the electrical energy to the sonic energy, that is ultrasonic energy. And this ultrasonic energy is transmitted to the tissues. Okay. From the tissues, again, this ultrasonic energy is reflected back, and this reflected back energy is again converted into the electrical energy by this ultrasound transducer only. Okay, the most important thing in this transducer is the crystal element. This crystal element is actually a piezoelectric crystal element, and this crystal element is located near the face of the transducer. The front and back of the transducer is coated by thin conducting film. Okay, and it is coated by thin conducting film, and it is in contact with these live electrode and ground electrode. Okay, it is in contact with two electrodes. The electrode in the outside is connected to the ground, so it is called as ground electrode. Okay, next, whenever there is some deformity in the crystal, whenever the voltage is applied across the crystal, so if this is the crystal and if you apply a voltage across the crystal, and this will result in deformity of the crystal, which is called as strain. The surface of the crystal is plated with gold and black silver electrodes. These electrodes are mainly made up of gold or silver electrodes. The outside electrode is connected to the ground to protect the patient from electric shock. Whereas, so this outside electrode is also coated with an insulated cover. The insulated cover is actually a watertight insulated electrical insulator is placed between the ground and the patient, so that the uh, current will not pass into the patient. Then the inside electrode, which is present here, live electrode, this inside electrode abuts the backing block. It will abuts the backing block. This hole is the backing block, so this inside or live electrode will abut the backing block. So this backing block will prevent the absorption. This it prevents not, it will absorb, the backing block will absorb the sound waves transmitted back into the transducer. This whole housing is actually made up of a plastic. There is also an acoustic insulator, and this acoustic insulator will prevent the sound from passing into the housing. So this is the acoustic insulator, and this acoustic insulator will prevent the passage of sound from this backing block into the plastic. Nowadays, a large variety of shapes of this transducer are also available. Now, let us learn how this transducer works. That is, the piezoelectric effects work. Actually, this piezoelectric effect is first described by the scientists Pierre and Jacques Curie in the year 1880. And what is this piezoelectric element? Piezoelectric crystal is actually made up of multiple numerous dipoles, and these dipoles are arranged in geometric fashion. They are arranged in geometric pattern. When an electric dipole is applied between the positive and negative end of these, when an electric dipole is an electric dipole is a distorted molecule, and this electric dipole, see, when a when a potential energy or voltage is applied between the two electrodes, that is the positive and negative electrode, this positive charge is present here, negative charge is present here. This current, when the current flows through this piezoelectric crystal, this electric field will align the dipoles present in the piezoelectric crystal. You can see the alignment of dipoles present in the piezoelectric crystal. So these two are electrodes. When the electricity is passed between the two electrodes, a charge or electricity will pass through this piezoelectric. Voltage is applied between the piezoelectric crystal, and piezoelectric crystal will change its shape. So whenever the voltage is applied between this between this in the piezoelectric effect, there is change of the shape. So if the voltage is applied in pulses, that is few pulses of voltage is applied, then uh, if the pulses of voltage is applied, then first there will be change of shape, and again it comes back to normal, again change, again normal. So that means this change in shape or coming back to normal, this will result in production of sound pulse. And this sound pulse is now transmitted to the tissues, and with the difference in their acoustic impedance, the sound pulse which is transmitted in the tissues will get reflected back, and this reflected back sound wave is also received by the transducer only. So when it is received by the transducer, when the sound reaches the transducer, the sound will now um, again this ultrasonic sound which reaches the transducer will provide a pressure, or it will compress the crystal element. Okay, the sound will compress the echoes, or the sound or echoes which are reflected towards the transducer. These echoes will again compress the transducer. When compress the crystal, that is piezoelectric crystal, when it compresses the piezoelectric crystal, so again a sound wave is produced, and that sound wave will now reach the backing block. See, when a sound wave is uh, enters, when this reflected sound wave strikes the piezoelectric crystal in a transducer, now piezoelectric crystal will get compressed, and when it gets compressed, it will produce an ultrasonic signal, and this ultrasonic signal is again transmitted back into the backing block. And also one more thing is that this live electrode will also take some of the live electrode which is present here. The electrode will, so this ultrasonic wave will induce current or electricity in the live electrode, and this electricity is transmitted through the cables, and from the cables the electricity goes into the computer or TV monitor, and in the monitor the image is displayed. So this is a just general ideology of how a piezoelectric effect, how based on piezoelectric effect the uh, transducer works. This piezoelectric chemical or this crystal element could be quartz. Some of the natural elements have this piezoelectric effect like quartz, but most of the crystals which are used in our ultrasonography are actually the man-made or artificial crystals. So this group of artificial crystals which have the piezoelectric effect are called as ferroelectrics. And the first element or first ferroelectric or first piezoelectric crystal is barium titanate, which is the first piezoelectric or ceramic ferroelectric. Whereas this nowadays, this barium titanate or all these are actually replaced by lead zirconate. Lead zirconate titanate. Lead zirconate titanate is the most commonly used ferroelectric or piezoelectric chemical in ultrasonography. The main advantage of this piezoelectric ceramic is that it can be deformed into different shapes. Based on the application which is needed, it can be deformed into different shapes. So if you see, this is the normal thickness of the piezoelectric crystal. So on applying the ones, when the receiving when the acoustic impulse, when the receiving or reflected sound echo reaches this reaches this crystal will vibrate. And when it vibrates, first it changes its shape. So and it gets vibrate. When it vibrates, there is vibration is seen, and this vibration can be seen either in thickness mode, where it vibrates like this, or it can also vibrate radially also. So there are two modes of vibration of this piezoelectric crystal. One, that is the thickness mode, that is it will vibrate like this up and down, whereas the other, radial mode, which where it vibrates in this different directions. Okay, when it vibrates, this vibration will convert the sound energy into electrical energy, and this electrical energy is taken up by the from the electrodes um, to the it is taken up to the display or computer, where the image is produced. Next, one more important thing is about the Curie temperature. As we have already said, this ceramic crystals are made up of many tiny dipoles. Okay, all these ceramic crystals which we have learned just now, like barium titanate or lead zirconate titanate, all these ceramic crystals possess piezoelectric property. They will have piezoelectric characteristics. But for the piezoelectric characteristics to work, all of the ceramic crystals should be arranged in these forms of dipoles. So they should be arranged as dipoles. But But to produce this polarization, first and foremost, this ceramic which is present here, this should be heated with the help of electricity. So electricity is provided, a strong electric field is provided to the crystal, and this ceramic is heated. Once the ceramic is heated at high temperatures, the dipoles will move and they align in the desired arrangement. They come to the desired arrangement based on the electric field which we have given to the ceramic. Then the ceramic is gradually cooled down, and so when it comes back to the room temperature, and when it comes back to the room temperature, now this dipoles will become fixed. So now the crystal will process the piezoelectric properties. So the temperature at which this crystal is heated to lose its polarization is called as Curie temperature. The temperature at which polarization is lost is called as Curie temperature. Heating a piezoelectric crystal above above this temperature will make this ceramic useless. Ceramic is become useless at this above this Curie temperature. So temperature above which the uh, ceramic will lose its polarizing properties or will lose this dipole properties is called as Curie's temperature. The next important thing is about the resonant frequency. See, this ultrasound transducer is designed such that it has a particular, each ultrasound transducer is sensitive to its natural frequency, to a characteristic natural frequency. And this natural frequency is actually determined by the thickness of the piezoelectric layer. This piezoelectric thickness will determine the natural frequency of the transducer. So this thickness is designed, this thickness of this piezoelectric crystal is designed so that its thickness is equal to half the wavelength of ultrasound to be produced by the transducer. So the thickness of the piezoelectric effect is equal to half the wavelength of the ultrasound to be produced by the transducer. The crystal will resonate, oscillate at the frequency based on its thickness. And the frequency at this thickness will corresponds to half of the wavelength thickness, and this frequency is called as fundamental resonance frequency. The frequency of a piezoelectric material at this half wavelength thickness is called as fundamental resonance frequency. Okay, so let us calculate the fundamental resonance frequency, okay, of piezoelectric crystal, that is lead zirconate titanium 4. Okay, if you see, the thickness of this crystal is around 0.001 meter, that is equal to 1 millimeter is the thickness, whereas velocity is equal to 4000 meters per second. So if you see, the crystal will resonate at a frequency twice the crystal thickness. So it will resonate at a frequency twice the crystal thickness. So if this is the thickness, it will resonate at a frequency, or sorry, the frequency is twice the resonant thickness. It will resonate at a frequency twice the crystal thickness. So frequency is equal to 2 into 0.001 meters, that is equal to 0.002 meters. We know velocity is equal to nu lambda. Sorry, frequency, not the wavelength. Sorry, this is completely wrong. Sorry, this part. So we have said that the thickness of the piezoelectric crystal should be half the wavelength. So thickness here is given as 0.001 into 2 is equal to wavelength. So wavelength is equal to 0.002. Okay. Now we know velocity is equal to nu lambda. Velocity is 4000 by 0.002 equal to nu. Nu is nothing but frequency. So from this we can calculate the frequency has almost 2 megahertz. So a 2 megahertz piezoelectric crystal is made up of at a thickness of 0.001 meters. So if 2 megahertz will give 0.001 meters thick crystal, so this is the important thing. Now what happens is, this crystal will oscillate, it will vibrate and it oscillates. When it oscillates, and this oscillating crystal is applied to two electrodes, so as a result, the frequency and wavelength of this oscillation should be carefully matched. Okay, this is about the frequency. There is one more important thing about the characteristics of uh, piezoelectric crystal, and this is called as Q factor. Okay, the this is Q factor of a transducer. Transducer Q factor. This Q factor refers to two important characteristics of piezoelectric crystals. One, it refers to the purity of sound, and second, it refers to the length of time the sound persists. One, it refers to the purity of sound. Second, it refers to the length of time the sound persists. So high Q transducer will produce the frequencies of the high Q transducers will produce narrow range of frequencies. Narrow range of frequencies. Whereas low Q transducer will produce high range of frequencies or wider range of frequencies. It produces wider range of frequencies. So this high Q transducers, they vibrate for a longer period of time. You can see they are vibrating for a longer period of time and they have a little difference. Okay, the interval between the initiation of wave and the complete cessation of wave. This interval between initiation of wave and complete cessation of wave is called as ring down time. And this ring down time is more for high frequency, high Q transducers, where it is less for low Q transducers. So Q factor will tell us about the purity of the sound and also the length of the time at which the sound is present. So when an electric pulse is applied to the crystal, this electric pulse will cause the crystal to vibrate. So this vibration will produce the sounds at frequencies a little. This is the frequency, actual mean frequency. So you will see that the sound waves are produced a little above the frequency and also a little below the frequencies. So Q factor will describe the frequency response, how the frequencies are present and how are they decreasing with time, or whether they are progressing or whether they are decreasing. So there is a formula for Q. Q is equal to resonating frequency, which is F naught by frequency above the resonating frequency at which intensity is reduced to half. This is the F2, this is the F1. Okay, above the resonating frequency where intensity is reduced to half, this is I2 is I1 by 2. Whereas F1 is above the frequency below the resonating frequency where the intensity is reduced to half. So if this is the intensity of X-rays, almost there are many ultrasound beam are present, and when the intensity is reduced to half, we have to see that point, and the frequency above which the intensity is reduced to half and the frequency of the transducer beam below which the frequency is reduced to half is called as, we call it as, we together, if we subtract these both and if we divide it by the actual resonating frequency, then we get the Q factor. Okay, now there is a graph which illustrates the resonating frequency for different Q factors. If Q factor is 20, Q factor 20 will generate this type of curve where there is narrow range of sound frequencies. Very narrow range of sound frequencies are present for Q of around 20. So this narrow range of sound frequencies will have a long ring down time. And this type of systems where Q is more is used for Doppler systems, Doppler ultrasound transducers. Whereas this is the curve B, which is broader Q frequency. And this broader Q frequency, that is Q is equal to 2 and there is broader curve, and this broad frequency range is seen. This broad frequency range has shorter ring down time. The ring down time is shorter, and as a result, this is mainly used in organ imaging, that is pulse echo operation. Okay, now actually what actually happens is that if you see the transducer, there is only one piezoelectric crystal. There is a piezoelectric crystal, and this piezoelectric crystal will produce sound waves and it will also receive the transmitted echo. See, what actually happens is this piezoelectric effect, because of this the crystal which present in the transducer, it will produce sound waves, and these sound waves will go into the tissues. and they penetrate the tissues. At each tissue will have its acoustic impedance. So based on the acoustic impedance, these sound waves will transmit. Some will transmit deep, some are only till the superficial part, and some of them will transmit it, and some of the rays will get reflected. So these reflected rays reach back the transducer, and these reflected rays which are received by the transducer will again vibrate the transducer, causing the signal intensity, electrical signal, and this electrical signal is sent to the computer where the image is displayed on the screen. But here the problem is that the this crystal, that is piezoelectric crystal, cannot transmit the sound, or it cannot act as transmitter and receiver at the same time. So if you give continuous sounds is given continuously, this piezoelectric crystal will vibrate and produce lots of uh, waves, ultrasound waves, but it does not have time to receive it. So if it does not receive the signal, obviously the image could not be produced. So the returning signals will be lost, and when the returning signals are lost, then obviously the image intensity and image is not good. So there is a thing, there is a one there is one value that you have to measure to see that the proper number of waves are reached will reach the transducer also. This is called as spatial pulse length. The spatial pulse length is actually the number of waves. If you multiply the number of waves with wavelength, then you get the spatial pulse length. Then the next important thing that you have to learn is about the backing block. Backing block will shorten, will absorb some of the vibrations, and it will shorten or decrease the sonic pulse. If the wavelength of the sound at the transducer is around 0.5 millimeters, the pulse is received. So if the wavelength is 0.5 millimeters, so this will go to the tissue and it will receive back. When it is received back, the pulse is received after two wavelengths. Okay, number of waves are two and wavelength is 0.5. So the receiving one's space pulse length here is around 2 into 0.5, that is equal to 1 millimeter. So ultrasonic pulse should be of single wavelength. So this backing block, generally in an ultrasound, in a normal ultrasound imaging in our transducers which we use in any department, there will be 2 to 3 cycles will occur between 500 to 3000 pulses per second. There will be 500 to 3000 pulses of ultrasound beams which are received by this transducer. All of them should be received by the backing block. The backing block will absorb all of this energy. So this backing block should be able to absorb all of the sound energy. So this backing block is mainly made up of tungsten with rubber powder in epoxy resin. Tungsten and rubber powder in epoxy resin. The ratio of tungsten to resin will mainly satisfy the impedance requirements. Okay, so this is about the ultrasound crystals. The next important thing is about the characteristics of ultrasound beam. So there are some important characteristics that we have to see about the ultrasound beam. One, whenever the two ultrasound beams are traveling in opposite directions and they might the two waves approaching each other, and in B they both are approaching each other but they are not overlapping. And if you see in C, they both this part of this, when they both overlap, these both are in opposite directions. See, this is going like this whereas this is going in like this. So both these, because they are at opposite direction, they both cancel each other, and as a result a flat signal is produced. Whereas here both of these waves which are traveling in opposite direction overlap with each other, and they produce, there is increased frequency or increased height is seen. Okay, whereas here again there is decreased height, there is cancelling is seen, and here they both will go back as separate waves. So these are the main properties of piezoelectric effect, where both waves of same amplitude overlap, it produces a bigger wave, and both waves of opposite direction will overlap, this will decrease, result in cancelling of the signal. Then there is one more thing where there is superimposition of wave fronts. Here if you see, this is the waves which are generated in the beginning. They are just 1, 2, 3, 4, 5 vibrating points, and each points are producing concentric circles or waves. Slowly, as I say, all these are actually parallel to each other in the beginning, but as they move away, as you see moving them away and away from each other, the distance at which the waves will become synchronous with each other. Slowly, the waves are touching each other and they are becoming almost like a same single line, right? So, this distance at which these waves become synchronous to each other will depend upon their wavelength. Okay, this is also one of the property of ultrasonic waves. One more important thing in ultrasonic waves is that the here, if you see, till this part, the waves are parallel to each other. These waves which are produced from five points are seen parallel to each other. From here, the parallel is almost lost. Okay, that is, at least for some distance, the waves will be parallel to each other. This parallel zone is called as zone of Fresnel, and the diverging, here they are becoming diverging to each other, and this diverging point is called as wave of Fraunhofer. Okay, so in ultrasound beam will consist of two zones, zone of Fresnel and zone of Fraunhofer. This zone of Fresnel is the parallel component which is called as near or Fresnel zone, whereas the diverging component of beam is called as Fraunhofer beam. And X dash is the area where is the notation where there is transition of beam from the parallel beam to the divergent beam. Okay, then there is a formula for finding out the length of the Fresnel beam. This length of the Fresnel zone is mainly determined by the square of the radius by wavelength. Square of the radius by wavelength will give us the length of the Fresnel beam. Then one more important thing is about the transducers and the Fresnel zone we will see. In this image, if you see, in the first image, in all these images, the size of the transducer is constant, that is 1.5 centimeters only. The frequency of sound is increased from 1 to 3 megahertz. So you can see there is increased frequency is seen, but the size is constant. Okay, when the increased frequency is seen from 1 to 3 megahertz, the near zone, which is the Fresnel zone, is seen to increase. Slowly, the Fresnel zone is increasing as the frequency increases. So, as the frequency increases, we can see that the Fresnel zone or near zone increases. So, elongation of the near zone is seen with increasing frequencies. Next, the next important thing is next one. Here, if you see, the frequency is constant. In the next image, we have made the frequency fixed at 1 megahertz. So, here we are increasing the size of the transducer. So, size of the transducer is increased. As you try to increase the size of the transducer from 1 to 2.5 centimeters, again the near zone increases. So there is increased near zone is seen with increasing the size of the transducer. So whenever the frequency is increased or size of the transducer is increased, there is increased near zone or Fresnel zone is seen. So, so when you use this high frequency transducer, whenever you use high frequency transducer, there are two advantages. One, there is longer Fresnel zone, obviously, and there is resolution is also good. On increasing the Fresnel zone, resolution is good and there is longer Fresnel zone. Right? Next. So one important problem of Fresnel zone is of this high frequency transducers is there is decreased penetration. Okay, high frequency transducer will show decreased penetration. Penetration is increased, penetration is seen in low frequency transducer. Low frequency transducers, whenever you see, they will penetrate better when compared to high frequency transducers. Okay, next. So if you see, this is what is this theta? Theta is actually angle of the angle where the Fresnel zone and the Fraunhofer zone are changed. So this change of angle, this is the angle at which the Fresnel zone is converted into Fraunhofer zone where the divergent is started. So this is dispersion of angle of far zone. This theta is called as dispersion angle of far zone. Okay. This is given by the formula sin theta is equal to 1.22 lambda by d. So these are the important properties about the transducer and the changes in Fraunhofer and Fresnel zone. Thank you.